Hello and welcome to the 22nd lecture. So we're going to continue this topic of how the gradient affects the graph of the function, and we will consider this example. So we have this function f of x, which is x to the 2 over 3 times 6 minus x to the 1 over 3. And in this case, the gradient and the second gradient are given to us. We could calculate them, but we will save time and use the fact that they are just given. So the gradient is 4 minus x, x to the 1 over 3, 6 minus x to the 2 over 3, and the second gradient is minus 1 over 8, x to the 4 over 3, 6 minus x to the 5 over 3. Okay, so these examples are similar to the ones we did before, but they are more intricate because the gradient and the second gradient will have points where they don't exist, right? And we're going to have to take account of that somewhat carefully, and that's going to change the picture that we create. So warning, this is a step above what we've done before. This is a subtle and difficult topic, and you might have to watch this a couple of times to get it to feel comfortable with it. However, this is an important topic, so after this particular topic, we have one more topic, L'Hopital's rule, before the second midterm, and then we'll discuss a section which is curve sketching, which will be putting the stuff we've learned together with L'Hopital's rule to get even more complete ability to sketch a graph. So we're going to need to learn how to curve sketch to quite a high level. We're going to spend a lot of time on that in total, and it's more efficient to get good at it as quickly as possible, which is why we're going to do these more challenging examples now and be in a better position when we go on to the section which is fully on curve sketching in one section's time. All right, so this is our guide, and we want to sketch this, and by that I mean find out all the information, i.e. intervals of increase and decrease, local mins and local max, and then intervals of concave up and concave down, and then points of inflection. Okay, so when I say sketch from now on, that's what I mean. I know we're going to learn all of that stuff. Okay, so solution. All right, so just as before, we're going to start off with the 0th order information, which is the information we can get without taking any derivative. So 0th order info. Okay, so look at our function. What do we see? We see that f of 0 is 0, f of 6 is 0. Let's think about the large-scale behavior of our function. So, okay, perhaps first a little kind of a recap on roots. So recall that if we, so let's put it over here, recall on roots. So note, if we take the square root of 4, then that is plus or minus 2, right? Because when we square minus 2, we get 4, right? But if we take the third root of, say, 8, that can only be 2. Because if we have minus 2, when we multiply by itself 3 times, we have minus 8, which is not the right thing, right? So there's only 1/3 root, right? And indeed, the third root of minus 8 is minus 2. So third roots are in some sense easier, and the same is true for fifth roots, seventh root. Any odd-ordered root is going to have one unique thing that is its answer, and it's going to preserve the sign. So if we have the third root of a negative number, it's going to be a negative number. The third root of a positive number will be a positive number, and that's true for any odd-ordered root as well. Whereas the square root of 4, again, can be minus 2. So there's some ambiguity about which square root we are actually talking about. So that thing will become relevant for us right here, because we have here a third root, right? And what I'm going to do to understand this at a larger scale is I'm going to take x to be such that the absolute value of x is very big, right? So suppose mod x is very big, okay? Then this thing, then x to the 2/3, 6 minus x 1/3, kind of doesn't notice this 6, so it's really a lot like just x to the 2/3, then minus x to the 1/3. And as we just discussed, third roots preserve the sign. So this thing is just like minus x to the 2/3, x to the 1/3, which is just minus x. So at a very large scale, this thing is a lot like minus x. So it can start to block in some of the information that we have. So the point of doing this is to get as much information at each stage as we can, so that when we do the next layer of information, so when we go from the 0th order to the 1st order, if we've made some sort of mistake in our calculation of the first derivative or later on of the second derivative, then the information we get won't be consistent with the layers that we've put in before from the previous layers. So in the case of the second derivative, from the layers of information from the 1st order and from the 0th order. And in the case of the first derivative, from the information we put in from the 0th order. So I like to put in as much information as I can from the 0th order before I take any derivative, before I do any calculation. So I have this check that I'm not messing anything up by some small kind of just stupid error and putting stuff on the graph that can't exist. So that's why we're doing this. That's why we're being so careful. So we know that we are 0 at 0, so across like this. We know that we are 0 at 6, so here we are. And we know that out towards either minus infinity or infinity, where the absolute value of x is very big, then we're kind of like minus x. So this is like minus x over here, and this is minus x. So out that way, we look like that. Okay, so that is all the 0th order information I can easily harvest from this. All right, now we'll do the 1st order information. Okay, so 1st order. All right, so we have the derivative given for us, so that's easy. We're gonna try and find, we're gonna succeed in finding the critical numbers. So the critical numbers are, again, the numbers where either the derivative is 0 or it does not exist. So we see straight away that the derivative is 0 when x equals 4. So critical numbers. And that's the only place the derivative is 0. But the derivative will not exist when we have x is 0, because when x approaches 0, this thing is like 4, this thing is like 6 to the 2/3, and this thing will be like 0, depending. It'll either be a very small positive number or a very small negative number here. So it's going to blow up to infinity if we approach from the right-hand side, and down, blow up to negative infinity if we approach from the left, right? Either way, it's definitely not existing at 0. So We have a critical number at x equals 0, and that looks too messy. Critical number x equals 4, comma 0. And where else do we have a critical number? A critical number when x equals 6, because again, this thing right here means the derivative does not exist. All right, so outside of these three numbers, we either have the derivative exists or it's non-zero. So let's put them on the graph. So this is 0, this here is 6, and this is, say, 4. So from minus infinity to 0, the gradient exists and it's non-zero. So it can't possibly change from being positive to negative from anywhere from minus infinity to 0, because if it did, it would have to cross through the x-axis, and there would be a point in this interval from minus infinity to 0 where the derivative is 0, and that's not the case because we've found them all. That would be a critical number, and these are the only critical numbers. So we know for sure that the derivative is either positive or negative on the interval minus infinity to 0, right? So let's start to put this stuff in a table, because we're going to try and find if it is positive or negative, and we know that it has to be one or the other on minus infinity to 0. We also know it has to be one or the other on 0 to 4 for the same reasons. If it wasn't, if the derivative went from positive to negative somewhere on this interval from 0 to 4, then it would have to cross the x-axis. There would have to be a point where it's 0. That's impossible. So it's either positive or negative. And then 4 to 6. And then 6 to infinity. Okay, and let's look at the factors we have on the first derivative. We have this 4 minus x. That's the first factor. We have a factor which is x to the power 1 over 3. Yeah, and then we have this factor which is 6 minus x to the 2 over 3. And you might be objecting that I don't have x to the third, I have 1 over x to the 3, which is true. But the sign of 1 over x to the 3, the sign of 1 over x to the third is the same as the sign of x to the third, right? So it's enough for me to look at the sign of this thing, because that's going to be the same as the sign of 1 over x to the 3, right? And I'm just going to save writing and have a neater looking table if I just put the simpler expression of the factor I need. So I'm going to keep it like this, because that's good enough. And then the product of the sign of this will give us the sign of the first derivative. So I'll put the first derivative here. All right. Now, the first factor should be easy to figure out. If we have 4 and we subtract a negative number, it's positive, right? 4 subtract a number between 0 and 4, still going to be positive, right? Because 4 minus a number less than 4 is positive. 4 minus a number bigger than positive is negative, so these guys are negative. Okay, here is where we don't want to mess this up. So this is the x to the third, right? And as we just discussed over there, taking the third root preserves the sign. So if we have a negative number and we take the third root of it, it is going to be negative. No? It is unambiguously defined, and it is going to be negative. Here, it's going to be positive. Here, it's going to be positive. Here, it's going to be positive. All right, so if you're not quite comfortable with x, with this little explanation here, just play with it a little bit. Put in some numbers. Convince yourself that when you take a third root or a fifth root or whatever root, which is 1 over an odd number, you will get that the sign is preserved through that process. Okay, and then here, all right, so we have 6 minus x to the third, but then everything is squared because it's 6 minus x to the 2 over 3. So whatever we have in here, when we take the third root of it, the sign's preserved, but then when we square it, it has to be positive, right? So it doesn't really matter it absolutely doesn't matter what's inside these brackets, because whether it's positive or negative, in the end, this expression has to be positive. So this is always positive, like this. And that gives us all we need. So we have positive, negative, positive. So it says negative, positive plus positive, positive, negative plus positive, negative, negative. Okay, so minus infinity to 0, it's an interval of decrease because slope is down. 0 to 4, increase. 4 to 6, decrease. 6 to infinity, decrease. Let's see if that connects with what we have. So we know it is out over here towards minus infinity, and it's 0, and it's decreasing from minus infinity to 0, so that makes sense. Let's block in roughly what we have here. And then what else do we know? We know from 0 to 4 it's positive. That makes sense too. You can believe that. It goes up like this. 4 to 6 goes down. I agree. And then it keeps going down. So, and that does make sense because it's connecting up with that stuff over there. Okay. But we can be more precise, right? Because we know some stuff about the derivative. We know the derivative is 0 at 4. So it's actually flattening out over here. Like this. And what else do we know? We know that we have stuff happening when x is getting close to 0. So let's try and figure it out. So again, I like to get as much out of whatever layer I'm at. So the first order, I'd like to get as much out of the first order information I can. And I can see there's some stuff about the derivatives that I can check out at these critical numbers. So let's look and try and see what we get towards 0. So if we take the limit as x goes to 0 from the right-hand side of this expression, f prime of x, so as x goes to 0 from the positive small numbers, then on the top it's more and more like 4. This thing is more and more like 6 to the 2 over 3, it's a positive number. And this thing is a very small positive number, because again, the third root preserves the sign. So we have 4, and then some number, 6 to the 2 over 3, whatever that is, multiplied by a very small positive number, right? So basically it's 4 over a very small positive number that gets smaller and smaller and smaller, so it's blowing up to infinity, right? So this thing is blowing up to infinity. And if we look from the other side, then again on the top it's like 4, on the bottom it's like this number 2 to 6 to the 2 over 3, but now this is a very small negative number. So this entire expression will be like 4 over a very small negative number, so it's going to be blowing down to negative infinity. Okay, so what does that conform with what we expect? Yeah, because we know the gradient is positive, and what we can now put in is that we have this kind of a shape, like like this, as if it was a root power curling in like this. And also on the other side, it is more and more like negative infinity, so it's kind of curling in like this, right? So that the slope is more and more like negative infinity as x approaches 0 from the left-hand side. Okay, let's do the same with 6. So as we, picture's getting crowded, maybe put it over here or down here. So the limit as x goes to 6 from the right-hand side of this guy, what happens? So if we go from the right-hand side, so this is a very small positive number, this thing means it's positive no matter what. So on the top here, we're going to have 4 minus 6, it's like minus 2, and this thing is just the third root of 6, some positive number. So we have minus 2 over a very small positive number, right? Yeah. So minus 2 over a very small positive number, this is going to go to minus infinity. And if we go from the other side, the same thing will be true. Because this thing is, because it's 2 over 3, this thing here will always be positive, right? Just as we talked about before, this thing here will always be positive. So if we approach 6 from the left-hand side, then this now is a very small positive number, but it's positive anyway. So this, no matter what, is a very small positive number. this on the top is still going to be an awful lot like -2, and this is just some number, third root of 6. So we have, again, a negative number over a very small positive number, so it is still going to be minus infinity. And let's see if that makes sense. Yes, it does, because we know that we're curling down like this, going through 6. So what that says is that we curl down very steeply like this, and as we go through 6, we are very, very steep. But because we ultimately are going to be like -x, then presumably we're going to be less steep as we go forward, like this. So expecting something like this, and then something like this, in order for this stuff all to make sense. Okay, so that's all we can extract from the first order. Now the second order. And we've got the second derivative given to us there. This time we're gonna look for the points where the second derivative either does not exist or it's equal to 0. And that is not a critical number, because critical numbers are the numbers for which the first derivative is 0 or doesn't exist. But it is some kind of thing similar to a critical number. So, but nevertheless, do not call it a critical number, because we have to be precise in our language. But morally, we're doing a similar kind of game, because we're trying to find the intervals where the second derivative is either positive or negative by identifying the numbers for which this thing either doesn't exist or is equal to 0. And outside of those numbers, we have an interval where it's it's always existing and it's never 0. So it's either going to be positive throughout that entire interval or negative throughout the same entire interval. So the principle of analyzing it is very similar. So let's see what we have. So I don't see that I don't think this is not 0 anywhere, but I do see that that we have an issue that it doesn't exist when x is 0 and when x is 6. So we're going to create a table like this, and then our first interval is -infinity to 0. The next one is 0 to 6, and the next one is 6 to infinity. And then we put the factors. Now, it's very easy to forget this -8 here. So that would be a kind of classic mistake I would make. So I'm going to avoid that mistake by putting in -8 as one of the factors, even though it's a really boring factor because it's always just a number. But knowing myself, I'm specifically trying to avoid making that mistake. You can do it a different way. You can, for example, just put a minus in front of this. That would be a more efficient way to do it. You wouldn't have to write so much. But let me do this the pedestrian way, just because I want to make this as easy as possible, particularly for people who've never done this stuff before. Okay, and then I'm going to fill out this stuff. Okay, so we have the third root of x, but then we're taking to the power 4. So again, the third root's going to preserve the sign, but when we take anything to the power 4, it's going to be positive. So this is positive, positive, positive. Nothing to think about really here. Here we have stuff to pay attention to, because if we take the third root, it's going to maintain its sign, but then to the power 5, it will still maintain its sign, right? So this 6 minus 5, whatever sign that expression is, 6 minus 5 to the power 5 over 3 will have the same sign. Yeah? So we just have to think about the sign of 6 minus, it's not 6 minus 5, it's 6 minus x, excuse me. 6 minus 5, the sign is very easy. Let me say that again. So this thing here, 6 minus x to the power 5 over 3, whatever is inside here, the 6 minus x, will have the same sign as 6 minus x to the 5 over 3. So we just need to think about the 6 minus x. Okay, so if we have x, which is between minus infinity and 0, then x is negative. So 6 minus a number. So let me say that better. 6 minus a negative number is like 6 plus a positive number. So it's positive. Now we have a 6 minus a number, which is between 0 and 6. That is still going to be a positive number. And then 6 minus number, which is bigger than 6, is a negative number. So negative here. Minus 8 is always minus. And then we have our factors. This is minus, and this is plus. All right, so if we've done this right, then we should be able to fit the information on the graph so that from minus infinity to 0, we are concave down. And then from 0 to 6, we are still concave down. And then from 6 to infinity, we are concave up. Let's see if that makes sense. Well, it certainly does. Because out here, it's like minus x, so it's going to have a gradient minus 1, right? But here we have a gradient which is getting closer and closer to negative infinity. So we can have something which is kind of like going like this, where the gradient gets more and more negative. In other words, the gradient is decreasing, i.e. it is concave down. Yeah? And it sort of flattens out like this as we go up. And we have it concave down from 0 to 6. That too makes sense. We can connect it up like this. And so here we have the gradient very close to infinity, positive infinity, then it's less and less big, less and less positive, 0, and more negative, then here close to negative infinity. So yeah, it's decreasing gradient, concave down. And then here we have a gradient which is very close to negative infinity, but it has to get towards this gradient, which is like minus 1. So it has to increase, so it has to be a kind of concave up shape like this, and everything fits together. And just to reassure yourself, just put the tangent lines on the graph to make sure you can fit them where they should be. So on the concave down, the tangent lines are above, of course. Yeah. And on the concave up, tangent lines are underneath. And that's what we see happening. So everything is fitting together. This is a consistent picture. We believe it. All right, couple final things. We have to talk about local maxes and local mins. So local maxes and local mins happen above a critical number if they happen at all. Right? If we look at the critical numbers, we have 0 for 6, right? So we already have the graph, but let's just look at this thing. So if we look at 0, we go from negative to positive. So with your hand, go negative to positive, negative to positive. You would expect a local min at 0. Yeah? So local min at 0. Okay, at 0. And we have another thing happening at 4 where we go from positive to negative, positive to negative. So that's the local max. Oops. At 4. Okay, let me put it over here, at 4. But notice I'm saying at 4. I'm not saying what the local max is. The local max is the value when we stick in 4 into this function f. So local max is, and I'm not going to try and calculate it. So it's going to be 4 to the 2 over 3, 2 to the 1 over 3, whatever that is. That is our local max. That's the height we are here. It is at 4, but the local max is actually the value on the y-axis, right? And the same, the local min is at 0, and at 0 it is 0. So local min is 0. But I do that 1 second because I don't want you to mix up where the local min is at as opposed to what the local min is. Okay, in this case they're the same, but obviously not always, not in this case. Okay, so that's local mins and local maxes. Final thing is points of inflection, where we go from concave up to concave down. Okay, that happens when we have a change in, let's look at this table, when we have a change in the second derivative. It's only going to happen as we cross through 6, yeah? And then we're going to go from concave down to concave up, yeah? So the point of inflection will be 6, f of 6 on this graph, which is right here, so it's just 6, 0. So this thing 6, 0 is the point of inflection, P of I. Cool. And a point of inflection is a point on the graph that has its x and its y coordinate. All right. I think that's it. I think that's everything. So notice that this only makes sense because we have this discontinuity in the first gradient. So normally if we have something which is concave down, then we can't have it. If we have something which is concave down, then we can't have it do a little kind of change and do a local max here, right? And unless we actually have a discontinuity in the gradient where the gradient jumps from here, which is like close to negative infinity to positive infinity, and then it can happen. So if we had a function where the gradient was continuous and it was concave down, then the gradient has to just keep getting more and more negative, and it can't have any kind of interesting effects. It can't do anything like this. So this question is a kind of question that can trick a lot of people, because if they are not drawing the pictures, if they're not carefully verifying the pictures with the maths, they might be doing these kind of calculations and they go, okay, it's concave down all the way from minus infinity to 6. So they draw something that goes like this, and then it is somehow concave up. No, that's not the case, because it is not concave down from minus infinity to 6. It is concave down from minus infinity to 0, and then it is again concave down from 0 to 6, this and like this. So when I'm talking about problems generally, I'm saying that this is a language that is a language that we can use to describe pictures, and we do the stuff in the language and we draw the pictures and we go back and we do this dance backwards and forwards from the language to the pictures. In this case, literally, this subject is about drawing the pictures. So, so you should definitely be doing that, and specifically, you should be drawing the pictures putting as much information on pictures as soon as you can. So, put as much as you can from the 0th order, and then the first order, and then the second order. Don't do a bunch of calculations and then try and put them all together. Go to the pictures as quickly as possible to make sure this stuff makes sense. Yeah? Cool. All right, so we'll do another example after I clean this board. Okay, the next example is f of x is e to the 1 over x. Okay, and we're going to sketch this. And when I say sketch, again, I mean find out all the stuff we can possibly find out. So, solution. So we're going to find out all that we can from the 0th order. Okay, so let's put a graph right here. And let's see what we've got. So first thing that is easy to extract without taking the derivative is what's going to happen as x goes to either positive infinity or negative infinity, because as x goes to positive infinity, then 1 over x has to tend towards 0. Yeah? And then that thing is what we're going to stick into E. So I said a number of times that we have to, you people have to be familiar with the graphs of elementary functions. Very familiar with them. You have to be very comfortable with them because we use them all the time. And like this, we'll do a composed function of 2 elementary functions. And one of them is this function E. It's like this. This is e to the x, and the other function is 1 over x, which looks like this. You will save yourself a huge amount of time by being fluent in what elementary functions look like. The sooner you get to that position, the easier the stuff gets. So please, whenever you encounter an elementary function and you don't know what it looks like, stop and try and work it out. Don't type it into your graphing calculator, Wolfram Alpha, whatever. Work it out. If you work it out, then you'll have it in your brain. That's the way you become familiar with it. Don't try and memorize pictures. All right, so these are our guys, right? So as x tends towards infinity, going out this way, 1 over x is tending towards 0. Yeah? And then we're putting this number 1 over x into e, right? And as x tends towards infinity, 1 over x is very close to 0. We're putting a number which is very close to 0 into e. So in pictures, we are taking some, let's say we go towards positive infinity. We are taking some number out here, okay? And we're putting it into the machine 1 over x, which gives us some little number here, right? And then we take this guy and we stick it into e, which puts us around here, yeah? So we take our x, like this. X goes to 1 over x, x to 1 over x, and that goes to e to 1 over x. This thing gets plugged into this. And we see the further out we go in this direction, the smaller we get, and therefore the closer we are to 0 here, and then the closer we are to this thing, which is just e of 0, which is just 1. All right? So we see that the limit as x goes to infinity, e to the 1 over x is just 1. And the limit as x goes to minus infinity, same game. So if we go towards minus infinity, it's one more like this, right? So over here is somewhere like minus infinity, right? And then 1 over x is going to send something which is close to minus infinity to a very small negative number somewhere around here, right? And a very small negative number gets mapped to here, and then we put that into e to the x, and again we have that this thing is tending towards 1. So you could also just take your favorite large positive number. So say your favorite large positive number is 1,000. Then 1 over 1,000 is a very small number. So it's like 0.0001, right? And then e to the 0.0001, is very close to e to the 0, which is 1. Take your favorite very negative number, minus 1,000, that's minus 0.0001. Put that into e, and again, it's very close to 1, right? So this is stuff we can do. Not too bad. So let's block in that rough information. So we have that out here towards negative infinity, it's like 1, and out here is like 1. Okay. What else can we do without the derivative? Well, often it's good to examine things around 0. And here it's a little bit more subtle. So let's go towards 0 from the right-hand side. So if we go towards 0 from the right-hand side, so here we are, going towards 0 from the right-hand side, we're getting sent very close to infinity. Yeah? We're getting sent very close to infinity. So if we're here, this is us, then the first machine sends us way out towards infinity over here. And then we plug that into e to the x, which sends us even further out to infinity. So we can see that the limit as x goes to 0 from the right-hand side of e to the 1 over x is equal to infinity. And again, if you're not quite comfortable with this, just put in some numbers. Take your favorite small number, like x is 1 over, your favorite small positive number, like x is 1 over 1,000. Then 1 over 1,000, when we apply 1 over x to it, becomes 1,000. And then we put 1,000 into e, it becomes e to 1,000. It's a huge number. Yeah? And if we took 1 over 1,000,000, then 1 over 1,000,000, and we apply it to 1 over x, gives us 1,000,000, and e to 1,000,000 is huge, right? So you can be absolutely sure of these things, right? You don't have to guess these things. This is something you can be absolutely confident of when you work them out. So this guy we know. The other guy, when we take from the other side, it's a bit more subtle. So limit minus e to the 1 over x. Let's look. So as we approach 0 from the other side, then 1 over x is telling us closer and closer to negative infinity. Yeah? So as we approach here, so let's rub off this guy because we're not going in that direction anymore. So suppose we are here. And we are approaching 0 from the left-hand side, right? Then 1 over x is sending us close to negative infinity, right? It's making us a very, very negative number. So then we get sent over here, right? So this action from x, 1 over x, sends us from here down here, and we put that into the x-axis because we're about to plug it into the graph of e to the x, right? So we have a very, very negative number. We put it into e to the x, we have e to a very, very negative number, which is very close to 0. Okay, and again, if you are not quite confident about this, put in some numbers. Put in your favorite small negative number, minus 1,000. So 1 over x, when we apply it to minus, start again. 1 over x, when we start again. Our favorite small negative number is minus 1 over 1,000. So 1 over x applied to minus 1 over 1,000 is minus 1,000. E to the minus 1,000 is a very small number, right? It's 1 over e to 1,000, which is a very, very small number because e is to 1,000 is a very big number. All right, so we know that this is 0. So we have some information. We have that we are way up with a vertical asymptote way up here, and we have that somehow this is like 0 here in some way. So we have to sort of connect these pieces here. All right, that's the 0th order information. 0th order. Now we're going to do 1st order. We take the derivative of this thing, right? It's just the chain rule. The outer function is e to the x, and it's just itself. So e to the x applied to the inner function is 1 over x, and then we differentiate the inner function. If we differentiate 1 over x, we're going to have minus 1 over x squared. Yeah, just the chain rule. So the outer function again is e to the x, the inner function is 1 over x. Derivative of the outer function is again e to the x, applied to the inner function is this thing, times the derivative of the inner function. The derivative of the inner function is this. Cool. All right, so this is minus e to the 1 over x squared. So this is always a negative number, but it doesn't exist when, okay. We have an issue about what it could be when x is close to 0. Yeah, it depends which side we go to. So if x is getting very, very small and it's positive on the bottom, very small positive number. On the top, it's e to some very, very big number, so it's a very big number, so we have a very, very negative number overall, which is consistent with this thing. If we go from the other side, then it's a little bit more subtle. So we have a very small positive number here, but then we have a number which is tending towards 0 here as well. So we have something like 0 over 0, which we can't analyze right now. That is the point of L'Hopital's rule. So we're going to learn that in the next section. We're going to learn to figure out what happens as we let x approach 0 from the left-hand side. We'll be able to analyze what that limit will be. For the time being, we can't. But we definitely do know we have an issue when x is 0. We know that that derivative doesn't make sense, and therefore that's a critical number. And that's the only critical number, right? Apart from that, this thing is never 0. So the one critical number is when x equals 0. So crit number is x equals 0. And this thing, no matter what, is always negative, right? It's always negative, so we don't have to think too much. We don't have to make a table with these factors because it's simply always negative. X squared is always positive. E to the 1 over x is always positive, and we have a minus sign, so it's negative. But that makes sense to us because we have something which is out here like 1 and it's somehow decreasing, so that can certainly happen, something like this. And here we have something which is really, really close to infinity and it's decreasing down to 1, so that's fine too. We believe that as well. Okay, so that is all the information we have from the first order, at least all the information we can without L'Hopital's rule, which we don't know yet. So it's all the information we can get from the first order derivative. Now the second order. We take the derivative of this thing. Let's work with this expression. So I'm going to apply the product rule. I'm going to differentiate this thing. So I'm going to have 2x to the minus 3. And then so I differentiate the first guy, leave the second guy alone. And then I'm going to leave the first guy alone. I'm going to differentiate the second guy, but the derivative of the second guy is exactly what we just calculated. So we'll just put it straight here. Okay, let's clean up that expression. So we have got, oh, it's not minus, this is x to the 3. So it's 2x to the minus 3. So if I put x down here, then it's going to be x to the power 3. So let's clean that up. So there's 2 e to the 1 over x, x to the 3. And then we're going to have e to the 1 over x, x to the 4. And I want to comment on it, so I'm going to multiply top and bottom of this thing by x. And then I can also factor out e to the x, e to the 1 over x. And that's it. All right. So where do we have issues with this thing? Well, the second derivative will be 0 when x is equal to minus a half. So I should probably have called this something. So if we let f of x be e to the 1 over x, then the second derivative x equals 0 exactly when x is minus 1 over 2. And we're also interested when this doesn't exist, and this doesn't exist when x is 0, right? Because we definitely have an issue there, right? Because this thing will be something incredibly big on the top, and this thing will be 0 on the bottom, so yeah, it does not exist. When x equals 0. Cool. So our intervals that we have to care about are going to be the interval from minus infinity to minus a half, minus 1 over 2 to 0, and then 0 to infinity. And we could make a table, and just like we did before, but in this case, it's kind of unnecessary, because the only thing that's going to affect the sign will be this part right here, with this thing right here. Because e to the 1 over x is always positive, x to the 4 is always positive. So I just have to care about the sign of 2x plus 1 to determine the sign of the second derivative. Yeah? So the second derivative less than 0 for x which is less than minus 1 over 2, right? Because if x is less than 1 over 2, then this thing here will be negative, and that's clear, right? And after we bring x for x bigger than 1 over 2, but not equal to 0, it makes no sense, right? So it is going to be concave down from minus infinity to minus a half, and then it's going to be concave up from a half, from minus a half to 0, and then again it's going to be concave up from 0 to infinity. Okay, all right, let's see if that makes sense with us. So concave down from minus infinity to minus a half. Yeah, that does make sense to us because it's got derivative close to 0 here, where it's more or less like 1, and then it's going to decrease, so we're going to have it decreasing like this to something, and then we can also permit this to suddenly be concave up from minus a half onwards. So we can have something like this, and then it changes and starts to be concave up on this last little part here. That is possible. That makes sense. And then it is concave up from 0 to infinity. Yeah, that definitely makes sense. This guy has got derivative very close to infinity, and then it's decreasing, 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 and it's kind of flattening out towards infinity like this, because we know ultimately it looks more and more like 1. So that does indeed make sense. We can draw some tangents just to convince ourselves. So concave down like this, and then here we can have concave up, flattens out like this, and this is indeed concave up, concave up, concave up. Okay, local maxes and local mins. So if we look at the critical number, it's only at 0. If we look at the sign, then it is negative to the left and to the right. So definitely no local max or local mins occurring at 0. Yeah. Points of inflection, where we change from concave up to concave down, that's only going to happen at minus a half. So this thing right here is with coordinates minus a half, and then it's going to be e to the minus 2, right? Is the point of inflection. And that's the only point of inflection, because across 0, we are concave up and concave up on both sides. And that is this entire thing. That's this entire thing that we can learn about this guy. Okay, so as I warned you, this is a more subtle, a more challenging question than the ones we did last time. However, we're doing the same things. We're doing the same principles. We're looking first at the zeroth order information, then getting as much as we can. We're blocking it in, putting in the rough information on the graph. Then we're doing our first order, and if it's making sense, we can fit it in with the zeroth order information we put on the graph already. And then we're doing the second order, and again, if it makes sense, we can fit it in. The additional subtlety here is that we're dealing with functions which have critical numbers that are not only where the derivative doesn't, well, not only when the derivative is 0, but also where the derivative doesn't exist. And that creates more interesting kind of different type of graphs than we were dealing with before. But we can handle this additional wrinkle of complication. It's not such a big deal. However, if you've not done this before, this might seem like it's a difficult topic, but it's again just a matter of practice. Don't give up on this, because we're going to do this to an even more refined level going forward. So it's going to save you time to learn it and get good at it now. So so watch this over a second time if you need to, and and then try and express anything that isn't clear to you. Bring those questions to me in office hour, and we'll go over it. This will make sense to everybody who wants to understand it. Okay. All right. Have a great day. I will see you all. I'll see the Friday group on Friday, and I'll see you all next week.